All right, so roughly number 14 and 2.4 says something like, hey, you should notice that the logistic equation, this guy. So this is the logistic equation, which is a population modeling thing, right? You can rewrite that as a Bernoulli if you try. Right? I mean, it's not actually really hard. You just multiply it out and then subtract some stuff to the other side. Right? So like specifically, you would do, okay, so this equation is the same thing as P prime is AP minus A alpha P squared, right? Doing that old distribute thing. And then you could subtract the AP to the other side. Right? And now, if A and alpha are numbers, then that guy's a linear kind of thing, and this guy is a number times a P squared. Okay, so this is Bernoulli. Great. We could solve this using the Bernoulli kind of idea, right? We could like use variation of parameters in the homogeneous solution to this thing to solve this. But that would be really dumb. Because this thing's already separable. Right? There's no t's in it at all. You guys see that? So, like, I could just divide by all this stuff and integrate. And I would get some reasonable solution that's the solution for the logistic equation. You guys know where the logistic equation comes from? Did I skip that?
It talked about, it's like the Verhulst model.
Yeah, it's kind of this sort of thing. This is sort of the idea that if you let loose a population or an organism in an area, right? Like you introduce the invasive flying snake to the Columbia boulders, right? It will, for a while, grow exponentially because it will eat all the other stuff that's here and there's nothing to hurt it, and it has no population pressure because it's not competing against itself, right? So it'll undergo exponential growth for a little while, and then eventually the boulders will be infested with these horrible flying snakes, right? And they'll compete against each other for food, and so their reproductive rate will drop off, and they'll eventually tail out on the carrying capacity. That's what this guy is. You guys kind of with that? So that's like exponential growth for a little bit, and then tapering off as kind of interspecies competition picks up. The interspecies competition part here is sort of, okay, P prime, right, is proportional to this stuff. And this stuff is like the total population times something like how much of the total carrying capacity is taken up. You guys see that? Another way you could think about this is the population, the rate of change of population is basically proportional to the population except for some kind of interaction that might occur to the detriment of one of the members of that population. You guys cool with this? So, if you fiddle this around, you can figure out it's Bernoulli, great. But that sort of assumes the carrying capacity is always the same. You guys see that? Like this alpha thing that's kind of my stand-in for carrying capacity, that's always the same number if it's constant, right? How good is that? I don't know. Depends on how much the environment fluctuates. If these are seasonal beings, right? Like if you have a seasonal kind of cycle, then the carrying capacity might fluctuate a lot based on time. You guys see that? Or it might fluctuate based on like longer term trends, like if it's getting warmer or colder, or if the permafrost is melting or whatever, right? So it might be a better idea to kind of improve our model by saying, well, what if we put a function of t in here?
And is that a different variable than the P? Is it P of T as well?
The alpha is different.
Yeah, so really all this is me looking at this thing, and my original model here, and saying, well, assuming that thing was constant was kind of stupid. So what if I assume that's a function of time? Then I get this new model that's a little bit more complicated, right? Which is the one they're actually talking about you solving in the book.
So what's P a function of then?
Population's a function of time.
Okay, so it's also time.
Yep.
Okay, so T would be,
So these are P of T's, and this is a dPdt. Right, so
And
the
that T
rate
is
of
the
change
same?
of the population over time. What were you saying?
So that T is the same?
Yeah, so this T is the dependent, or the independent variable in this whole business. You guys kind of with me on that? Okay, so now that this thing's not a function of, well, now that this thing's a function of time and not a constant, this becomes more interesting. You see that? Like, now all of a sudden this is Bernoulli and not idiotically Bernoulli, like I just made it look Bernoulli. It's Bernoulli and you need to have it that way. It's not separable anymore. You guys kind of with that? Okay, so if it's not separable anymore, then you have to solve it using the Bernoulli techniques. Does that kind of clarify the motivation for this problem? Do you want to actually do this problem, or do you want to?
It's got an interesting twist with the constant we have to figure out. Let's see how you
Oh, I don't like the sound of interesting twist. All right, let's see if we can go find the interesting twist. All right, so what's your homogeneous solution?
E prime minus AP equals 0?
Okay, so your homogeneous equation.
Oh, that's right, yeah.
No, that's good. So your homogeneous equation is p prime minus ap is 0, right?
and then the solution would be e to the negative integral of a,
negative.
yeah, dt.
Isn't A
A is constant.
A is a constant. So this is e to the at. Okay. Yeah, that seems to jive with my intuition, right? Like if I don't have this forcing business going on, like if the carrying capacity doesn't matter, then yeah, it should be exponential growth. Let's go with that part. Okay. All right. Now, how do I try to solve this with Bernoulli technique? Like what am I trying to do?
Oh,
Like I found the homogeneous solution, right? Then what?
Y is U.
Yeah, then you should guess y is u times yh, right? Well, but I don't really have y's here anyway, right? I should be guessing. So translated into the variables I'm working with, I should be guessing
E equals U of T times pH.
p equals some u of t e to the at. You guys down with that? Okay, so then you take that and you plug it in to here. Oh, and please note that I have totally disregarded this, my original motivation. Because that problem was fairly easy to solve, so I disregarded it. So I plug that in here. Oh, except I need p prime, don't I? Okay, so here I'm going to have what we'll figure out is p prime in a second. And then I got minus a times u of t e to the at. And this is supposed to equal
Negative A
minus a
times alpha of T
alpha of t,
times B squared.
and then p is u of t, so I got u squared of t e to the 2at. You guys all on board with this? Okay, what was p prime?
A, U, e to the AT?
Okay, there's an a u e to the AT. Oh, I guess I was writing of t's here. Okay, so that's the derivative of the second thing times the first. And the other part should be u prime of t e to the AT. And everything freaking cancels per usual. So that stuff drops off. So you got u prime of t e to the AT is minus a alpha of t u squared of t e to the 2 AT.
Yeah, that's all.
Okay, and probably I'm just gonna, no, maybe I won't. All right, what do you do? I have vowels. Dude, I have all the vowels.
Nope, not mine.
Oh. Or E's.
Separate.
Oh no, I have
Yeah,
it.
you got E's, no.
I don't have any O's. I can multiply both sides through by O and call it a day. I think maybe I want to multiply through by e to the minus AT and u to the minus 2. Okay, so I got u to the minus 2, u prime. I'm dropping my dependence on t because I'm tired of writing it down. And on the other side, I got a minus a alpha of t. And then what?
U to the AT.
E to the AT. Okay. So then I should separate. So I should multiply both sides by dt and slap squiggles. So I got the integral of u to the minus 2 du is the integral of minus a times the integral of alpha of t e to the AT dt.
Parts?
I don't know.
That you don't have to evaluate.
Yeah, and you can't anyway, right? Until you know what a of t or alpha of t actually is. Like trying parts or something is like that's a good instinct to have. But like if alpha of t is e to the minus AT,
Then you're just getting arbitrary D.
yeah, you're just getting arbitrary garbage. So I'd just leave it like this and then leave the technique of choice later.
They want us to say assuming p is 0 equals p naught
Yeah.
greater than 0.
Yeah, then they want you to write this as a definite integral, like
Yeah,
a couplet.
and insert y, you get a minus 1 over p naught, they're constant. They break the integral up to 0 to t, that integral minus 1 over p naught.
Okay, let me get one more step and then we'll do that, yeah. So here I have the integral of u to the minus 2, which should be,
Negative u to the minus 1.
so I got a negative u to the minus 1, right? 1 higher power over the 1 higher power, equals,
Negative a times
That plus
that.
okay, so I got negative a, and then this is the part where I should rewrite this indefinite integral as a definite integral plus a constant. So I'm going to integrate from 0 to
T.
t, alpha of, what's your choice for a dummy variable? Yeah, tau I think would be the standard choice in this case. So alpha of tau e to the a tau d tau.
This would have forced you decimal point.
Okay, and then, so this dude here, right, is the antiderivative of that thing according to the fundamental theorem of calculus part 2, right? And then there's also a plus a constant. Okay? And now, algebraically, to simplify, you should at least do this.
You have to specify that that's an arbitrary constant with respect to u. Like, is there a way that they can mess up that formula somehow that we see as something weird?
No, that c should be a constant of integration. Who's they, Chris?
The jerk that came up with this.
Who's messing with your day, man? No, you can assume that anytime you see a plus C in a calculus class, that thing is a constant. Not a constant
Unless it's a
depending on
potential
something.
function.
No, calculus class.
But that was constant.
No, we put of y on those. When we were calculating potential functions, we made sure to say, this is a constant, well, except that it might depend on the other variable. Right, because it's constant with respect to something. In a one-dimensional calculus case, which is what I'm doing, that plus c is constant. Constant with respect to constants.
It's a constant.
Okay, so I think here, I know what u to the minus 1 is. So what's u?
One over that.
1 over that jazz? Oh, and thank God I erased the thing I started with. So I think I have u is 1 over this.
What's the relationship between P and U again?
The relationship between p and u. Good
Evidence.
question. Yeah, what was the relationship between p and u? So if I wanted to do this,
E to the AT?
yeah, there was an e to the at.
Yeah.
Oh,
Bam. Just like that. Okay, now, what's p of 0? Oops. Kind of gave that one away. Yeah, so you might assume that the population starts at p naught, right? So if you plug 0 in here, you get, on top you got a 1, and on the bottom you got a, what's the integral from 0 to 0? 0. So I got a times 0 plus constant. Okay, so I think I figured out that constant is 1 over p naught. Yeah? Cool. All right, so where should I plug the 1 over p naught? In for the c. Thank God for whiteboards. Right? Because otherwise I'd have to keep writing that integral with all the tau's in it over and over and over again. So I think ultimately this is what we've got. That is our kind of improved population model where the carrying capacity might fluctuate over time.
And they just multiply through by P naught.
I'm absolutely certain that they did. Up to algebraic simplification. This is what we put out. So it should be noted, yeah, that the alpha here is not quite the carrying capacity as I described it. Right? I said it's to do with the carrying capacity. It is not actually the carrying capacity. It's down with that? It's some kind of proportionality business. Cool? That sort of answer your question?